going to back to where we were, that spectral bias is everywhere. And the reason why it occurs, it can be derived, basically mathematically derived. Um, there's obviously one more step after this derivation, is that you need to generalize this for multiple layers, and for that um, you'd have to use math induction. So math induction used to be this, at least for Indian students, it used to be this 11th grade chapter that we all comfortably ignored back then, but it actually comes in useful here. So you induce over over n layers, and you'd find the same thing. Now, lingering on it for a little bit, this is true for generative models as well. What I'm showing you is a plot for a 3-layered QG system with a diffusion model. Basically, the theory is that if you have a flatter spectrum like moisture, you'd have lesser bias. For dynamics, you have larger bias. There was a very popular model that came out maybe a year back called GenCast, which used diffusion models for autoregressive rollouts and showed improved spectrum. That is theoretically not the case. Even any model basically whatsoever would have spectral bias, and the bias would depend upon the slope of the physical spectrum. So it's dependent on the actual physics of the system, but it's generally an artifact of deep learning models for any systems. Okay. One of my PhD students works on this. We have a full dedicated paper on understanding spectral bias for generative models. So for the next 30 minutes, I'm going to try to wrap up the theory and then try to demonstrate results at scale. Basically, if you remember the 3 prongs, we are in the hierarchical modeling part where we understand the problem, end to end. We can derive this problem from first principles. So that's, at least one step closer to science, one step away from traditional ML. And now we will try to fix it. And you realize that fixing spectral bias, you can do this with 10 different methods, and all of them are useless. I'll tell you why, but most of them are operationally still successful to the first order. So what are the things that you can do? Well, remember the spectral bias, which is why you don't capture the wave numbers, the high wave numbers, and then it's an autoregressive model. So you're rolling it out, you're taking predictions, plugging it back into the model. So this error is going to grow. So there's a temporal error growth that we just do not know how to quantify. If this was a finite volume method, you could write out equations based on your time integration scheme and define how error growth happens, and you can bound it and do all the things that a mathematician should do. Here you can't do any of it, but you know that it will grow. So what the way to fix this is going to be very simple strategies. By simple, I mean everything within first year mathematics, first year college mathematics, essentially. So the one thing that we would do is we are going to do what all climate scientists taught us how to do, is we are going to represent the tendency with a neural net. Again, what is this n prime? If you're Google, it's big. If you're me, it's small. But it's one neural network. Again, theories should be absolutely agnostic to architecture. It should be agnostic to training strategies. It should be agnostic to the type of loss functions and things like these. Okay, so it's one big neural network depending on what you can afford. And then let's do something that we have learned how to do in numerical analysis 101. Let's write out an integration scheme, but in a differentiable column. So it has to be a differentiable layer without any parameters that implements a higher order time integration scheme. So Euler is not higher order, it's the worst you can do. But still, in the context of machine learning, it's better than we were doing before this, which is replacing the entire right-hand side with a neural network. Don't do that. Represent the tendency like regular scientists, and then write an integration scheme that you've learned in a textbook. So let's go with something a little more sophisticated. Let's go with RK4. Again, it doesn't matter whether it's RK4, but and I'll tell you why it doesn't matter, because again, all of these should be explained. Now, you might be inclined to think, okay, now this, well, one, you might be inclined to think that this is all alchemy, and you'd not entirely be incorrect if you assume that. But if you're inclined to think, no, this is very rigorous, because now you're doing things like a numerical analyst. You're writing temporal integration schemes based on 100 or 20, I don't know, like 500 years of RK4 theory. So if you're thinking like that, I want to re-emphasize that's not true. Okay, there is nothing RK4 about having a differentiable layer that implements an RK4 strategy. because when you write RK4 where n prime is your tendency, so it has a diffusion operator and a reduction operator and so on and so forth, it's very different because you can actually write the stability map of RK4. Here, this is, you're still in a black box domain, okay? You have represented this with a neural network. As soon as you've done that, you have lost all senses of mathematical rigor. And all you have done is brought some intuition about how temporal schemes should work. So this is still in that same block of algorithmic intuition. This looks reasonable. I have not shown you anything where this is validated to be reasonable, or I have proven that this actually has certain properties that you would expect. But the intuition was that if you do things this way, and this is called continuous networks. Again, if you want to know the details, go to this paper, it's on arXiv. These are called continuous networks. If you do this, the hope was that you're going to gain some form of consistency in the same sense of Lax equivalence theorem, or temporal stability. Higher order methods are more stable. All of us know that, right? So something around that. Now, for spectral bias, what we would do is the simplest possible thing. Again, there are 10 different ways to fix spectral bias, okay? And I'll tell you why, and none of them are really useful. But the easiest way to do this is you calculate their spectrums and you write a regularization in spectral space. Look at how many wave numbers you're capturing up to KT, take all the higher wave numbers, take their Fourier transform, put it in as either an L2 loss or an L1 loss, typically an L1 loss. If you have Kx greater than Kt, then even L2 works. It's important to note here, if you put all the wave numbers in here, if you write this equation for all the wave numbers, then square it and add it in your loss function, it's useless because Parseval's theorem, right? Squares in Fourier space across all wave numbers is equal to the same quantities magnitude in physical space. So it has to be after the cutoff wave number, or it has to be an L1 norm. So it's a regularization in spectral space. And I'm sure either Jim or somebody talked about it as well in one of their applications. We call it spectral regularization. So simple strategies, right? Do something that takes care of the scales, and then ensure that your temporal scheme is something that you have at least read in a textbook. That's really the only two strategies.
Yeah, actually, sorry.
Go on.
Yeah, actually, it was more subtle. You took it was not just the spectral coefficients that are being regularized. Sometimes you can take the log so that the order of magnitude is given more importance.
Right. Okay, great. Yes. So
that's immediately not obvious that by Parseval's or any other theorem it will be useless.
Correct. So for if you actually take the log, then it does not conform to Parseval's theorem anymore. So if you actually take the log, in fact, more than the log, if you know the slope of your spectrum uphand, like up front, you can scale it so that all the wave numbers are equally weighted, right? But as a more general strategy, the idea is run your experiment once, see where you're getting cut off, and have a regularization strategy that matches the rest of the wave numbers. Now this is still useless. Why? Because suppose you run optimization over this loss function. I'm using the word useless as a very strong word. I meant to say that it still doesn't resolve our problem entirely. I mean, of course it's useful, but it doesn't resolve our problem entirely. Why? Because suppose you optimize this loss function on a single precision machine with 10 power minus 6 as your final error. That means your spectrum would still have 10 power minus 6 as an error. And you roll it out for thousands of time steps, chaotic multi-scale system, even machine precision error is going to curl back up. So essentially you need a mechanism to ensure that you don't have a bias at any of the time steps, which is where sort of this third prong comes into the picture. And the way you do this is with self-supervised learning. And again, this is a little complicated. I'll go over it. Here you have a regular network that has all your spectral loss and so on and so forth. And this is during inference, right? So you do this optimization during inference. So you are running a model with all the bells and whistles, an RK4 solver, a spectral regularizer, and so on. And then at every time step, you know what the true spectrum of the system is. The assumption, the blanket assumption is that you have a roughly stationary system whose spectrum slope doesn't change. So you have an L1, you have a loss function that optimizes over just the spectrum during inference. And then what you do is that you low pass filter this model. So you only look at the small scales, and you have an additional spectral loss only on the small scales, and then you add them back up. So that's the idea. We call it self-supervised learning on the spectrum. And what it really does, if you're a fluid dynamicist, this is really hyperdiffusion done neatly. That's really all that it is. It's just doing hyperdiffusion instead of an ad hoc cutoff that you use in hyperdiffusion. You do something a little more regularized, and you're doing this at every time step. And so this is essentially what we did for that intermediate complexity QG system. And then we ran that simulation for 300,000 days. So autoregressive rollout, no other physics, just these three things. Underlying architecture doesn't really matter. But for baseline, we have a regular unit, and we're plotting the long-term mean. So this is like climatological statistics. Of course, this is a simple system. There's no climatology per se. But so you're looking at the long-term mean of the stream function, the velocities, which are derived quantities as in terms of their derivatives, and looking at the PDF and so on. And over 300,000 days, the model remains stable and physically consistent in the sense that the long-term mean matches for both velocities and the stream function. The PDF still has a problem with the tails, but that's a different story for a different day. And the second order statistics, so the variance, which in the world of weather and climate we call, well, you guys are weather and climate people, so EOF1 and EOF2, they match for the system as well. So first order statistics, which is mean climatology, second order statistics, then principal component decorrelation and things like that. So we did this for QG. So again, we were in the hierarchical modeling phase. So we did this for QG. So take a model, put these three things that we thought were principal structures, all intuition, no math whatsoever, all intuition, just look nice, right? That RK4 thing looks nice. We never really proved anything about stability. But we put them in and we scaled it for a few different systems. This is era 5, 2 degrees, a few different variables, not the entire atmosphere. And we saw that we get the climatologies correctly as compared to any of the state-of-the-art AI weather models. Of course, the state-of-the-art AI weather models have much better performance, short-term, day 1, day 3, day 5 performance, but they're all crazy long-term. These fixes helps you think about climate models. It thinks about how you can go from the weather modeling sort of time scale to the climate modeling time scale. If you're a climate scientist now, you'd say, well, what about CO2 and all the other things? And we'll come to that. But basically, we can retain the spectrum. We get the spectrum perfectly as opposed to other models whose spectrums are all over the place. We get the mean climatologies correctly. Now, so this is still QG system and sort of a subset of the era 5 variables that we trained on with a very simple architecture, unit architecture essentially. So at this point, what we need to talk about is what are these things really doing? So this is where I think a science first approach comes into the picture. Now that we have something that works, it still hasn't scaled, right? I never talked about a climate model, but it was all intermediate complexity systems. Era 5 maybe, sure, but not really at the scale of a climate model. So the first thing that we're going to do is going to distill a theory out of it. What are these things doing? Are these things actually helping us build to at least a practical theory of understanding how machine learning models behave and whether we can predict its behavior? Because that's a big problem with these models. If you write a numerical solver for a PDE and you know what you're doing, you can tell me everything that might go wrong with that numerical solver. You know how to predict its behavior, not the system's behavior. That is a science that you're solving, but how the numerical solver is supposed to behave. You know everything about it. That comes with the rigor of numerical methods. Here, you have a 20-layered, 100 attention net transformer, and then you just pray to God that it works. And that's really not how it should go, right? So we need to distill a theory out of it. So the idea again is that we want to build a theory that helps us predict these models' behaviors. So can we say upfront whether one model would be better than the other? Can we say something about its stability? Does it make sense even to think about stability? And the only two things that we have, again, is an integration constraint that I talked about and a regularization in Fourier space and nothing else. So this is just a reiteration of what we have. So these are the two structures in this model. So think about it, you're writing xt at the next time step as xt plus some integration operator composited with the neural network. That's how you can write in a one-line math what the numerical integration operator does. Now, really, if you want to think about it, this is an explicit numerical integrator, right? And if you've done a bit of advection diffusion systems and things like that, you know that people use semi-implicit schemes and these kind of ideas as well, right? So the first thing we want to do is, let's see if we can extend it for implicit time integration as well, whether a thing like that is first of all possible, and then does it actually behave like an implicit solver, because we haven't showed any of that stuff yet. So to be able to pass it off as an implicit solver, the way we have to write it is that your predicted time step should be your previous time step, then your favorite choice of numerical 101, numerical analysis 101 solvers, neural network, but at the next time step. But you don't know what that is, right? That's why in a semi-implicit scheme, you have to solve a linear system of equations that estimate xt plus delta t. And that's where the whole scientific computing domain of preconditioners, linear solvers, all of that come in. Here, we are going to do exactly that, except we're going to do this in a clever way. How are we going to do? We're going to use the same principle as deep equilibrium models. If you're not familiar with it, don't worry about it. I'll just explain this to you. So we have something called an implicit layer. At each forward pass, it takes in xt, and then it solves for xt plus delta t in this equation using either a fixed point solver or Newton's method. This is a nonlinear equation at each forward pass for a fixed theta. Each forward pass, your theta is fixed. Next pass, your theta gets updated through backpropagation. So at each pass, I'm just going to solve this nonlinear equation from a textbook solver. In this case, it's a fixed point iteration solver, which means what? Initialize xt plus delta t with xt, and then just run this fixed point iterator until you don't see a change in xt plus delta t. That, in essence, is your implicit numerical integration constraint. It's more expensive because at each pass, you're solving this fixed point iteration. And there are ways to scale it up. That's not important. Mathematically, that's all you're doing. So it does add additional cost without any memory accumulation. Most of these models are memory intensive. It's a memory bound computation that you're doing, not a time bound computation. So now for any of these integration based constraints, if you look at the error analysis, and the kind of error analysis I'll do again is very textbook, exactly the way we learned linear stability analysis for nonlinear dynamical systems. You assume that you have a true system that you don't know. That's your weather system or climate system that you're trying to model with this G operator. That's your neural network. It's fancy. It's either fancy or it's not fancy with some constraints, etc., etc. Doesn't matter. You write them out. Remember, prediction goes in, prediction comes out. Truth goes in, truth comes out. At any point of time, the error epsilon t is essentially your deviation from the predicted trajectory and your true trajectory. You plug these things in, the models in, and then you write up as ut minus epsilon t. And then you do the simplest possible thing, you do a Taylor expansion. As soon as you do a Taylor expansion, you see that this adjoint terms comes, this Jacobian of the neural network with respect to the state of the system. This is a square matrix. This, in nonlinear dynamical systems or linear dynamical systems, is basically your stability matrix. This is the term that pops up. And this term, the one here, I'm assuming you can see my cursor, this term is basically the generalization error for one time step prediction of these models. That's how these models have been trained. They're trained to predict the next time step. That's all. That's how ForecastNet is trained, GraphCast, any of these models are trained. So this is just generalization error for one time step prediction, which is very low. These models are trained really well. So these errors are pretty low for any time step. That's the generalization error. So now you can define this generalization error as epsilon nu at t plus delta t and write out this nice upper bound that your error growth as a function of time is going to be upper bounded by this Jacobian spectral radius, which in layman's term means take your neural network, compute its Jacobian, that's a square matrix, compute its largest eigenvalue. Your error growth is bounded by your largest eigenvalue's magnitude. Well, of course, that's exactly what we learned in textbooks. So it should happen that way. I never assumed G is a neural network. I assumed it's any nonlinear operator. This is how it's supposed to work. The question now is, does these models conform to linear stability analysis? Do I really see behavior like this that conforms to this theory? And that is essentially what I'll speak about for the next, well, let's see how many minutes. So for a direct step model like GraphCast, ForecastNet V2, Pangu, all the other state-of-the-arts, we're calling these direct step models. You have a neural net F or whatever, a big neural net F. This should be U, sorry for the typo, this should be U. T plus delta T is F of UT. If I compute the Jacobian, it's del F del U. It's a huge matrix, but it's a square matrix. I can compute its eigenvalues if I'm lucky. Our set of models, which are these integration constrained models, are trained as ut plus delta t is ut plus delta t times favorite integration method of n. So the Jacobian of this quantity is an identity matrix plus this gradient term. Now this gradient term has no physical meaning if you look at it. What it does have is a delta t multiplied to it. So if your delta t is small, then your eigenvalues are going to be very close to 1. 1 is neutral stability. For more than 1, your model is, again, 101 dynamical systems analysis, more than 1 eigenvalues for discrete dynamical systems, you go crazy. Less than 1 eigenvalues, you diffuse down to 0. If you're 1, you're neutrally stable. So now if you look at an example plot of an RK4 based MLP and a regular means direct step model, here's the error growth of the direct step model. You see how it becomes unstable? We already know it becomes unstable. This is evidence. Here's the RK4 based method. The error growth is very small. Here are the eigenvalues of the direct step model. One of the eigenvalues is larger than 1. This is the one that contributes to this giant growth. What about these models? Well, the system I'm looking at here is a KS system, not important, but it has 1,000 eigenvalues. You can see 1,000 of them here, can't count, but for the black one, I only see 1 eigenvalue. Well, it's not really 1. What you see are 1,000 eigenvalues clustered at 1 with 10 power minus 6 as their standard deviation. And the reason why this happens is because delta t is small, this derivative is also very small. I won't get into that because that gets into random matrix theory and other sorts of statistical physics stuff that's not really relevant here. But basically, any model that looks like this, no matter what H is, Euler, RK4, P, C4, it doesn't matter, would always have eigenvalues that are clustered at 1. And the hope is those eigenvalues are diagnostic to us, which means I can just look at them and tell you which model is going to give me better performance, which model is going to go unstable, which model would have less spectral bias, and things like that. It has to be a practical theory, which means I should be able to compute something which is, first of all, computable. Eigenvalues are not computable objects, right? Especially for billion dimensional matrices. Largest eigenvalues are. So if it's the largest eigenvalue, then I should be able to compute it with randomized sketching, etc., etc. So that's the HPC things. Let's not talk about it. Science is, if I get the lambda max correctly, I should be able to tell you about models. So now comes the machine learning version of a mathematical proof, because you can't prove things anyway. So what we did here was we looked at 36 different models, different architectures, different loss functions, different integration schemes, implicit, explicit, everything put together, and plot everything on the same sort of panel. What we see is any model that doesn't have these integration schemes are bound to be doomed because they will go unstable. Any of these models that are integration constrained are going to be stable. They would roughly have the same error growth, and the error growth would be very low as expected, higher order stability. More importantly, all these models would have their eigenvalues clustered so closely at 1 that you cannot see the difference. There are 34 different models, 1,000 eigenvalues each, plotted here that you cannot decipher from one another because they're so closely clustered at 1. While the rest of the other two models, you can clearly see some of them have greater than 1 eigenvalues. So what we really showed here was that if you have this really simple integration constraint training, no matter how you fiddle around with architecture, plus functions, training strategy, even systems, I'm only showing you one system, even systems, you will always get this nice linear stability coming out of these models. It actually does conform to linear stability. It does conform to the classical linear stability theory that we learned back in college. And in fact, the fact that it does can be further seen in this plot where we derive a linear scaling law for these eigenvalues. Basically, these are all the clustered at 1 eigenvalues, very small. These are the ones that are above 1 that will eventually go unstable. Then I zoom into this portion and I look at all these other integration constraint models. All of them behave really well. They are virtually indistinguishable from each other. But still, if you were to put them under a microscope and ask me a question, still, amongst your best models, tell me which one is better. What you do is plot their largest eigenvalues. Whoever is up here is worse. Whoever is down here is good. The cool thing about this constraint is that you don't have to look at all the eigenvalues. You can really look at the largest. And the reason why you can look at the largest is because all of them are roughly equal to 1. So basically, this trace-based equality reduces down to an inequality. So you don't have to do an eigenvalue decomposition. All you have to do is compute J, and then you take the mean of the trace. This is a highly parallelizable object from random sketching. You can do Hutchinson's sketching algorithms and other sort of randomized sketching algorithms to compute these eigenvalues. Otherwise, for big systems, this becomes a problem, right? So that is the cool part about it, is that these eigenvalues are indeed predictive of the performance of these models. I talked about implicit methods, and here's sort of evidence that if you have an implicit solver, it's stable and everything. It's also better than an explicit constraint with a larger delta t. So what was implicit methods theory? It said that between an explicit method and an implicit method, if your delta t is larger, then implicit methods would have more stability as compared to an explicit method. It would have lesser error growth. This is essentially what we're trying to show here, is that for larger delta t, here delta t is about 100 times than sort of the DNS delta t of the system, like the actual simulated data is delta t. And it showed that implicit methods have lower largest eigenvalues than the explicit methods, which is why they have lower error growths and eventually renders you a better model in terms of performance. Key point to note, both of these methods in this case are stable and pretty good. If you were to really put, this is a theory, right? It shouldn't matter whether operationally you have got a model that works. The theory should be able to decipher between good models as well. The third question that we wanted to ask was, okay, are these eigenvalues predictive of spectral bias? So we take two architectures, a regular neural network and then a Fourier neural operator. The entire talk is devoid of any architectural specifications. What is an FNO? It's one of those other fancy architectures that works really well. One of the claims for an FNO is that it has better spectral representation of systems on which you have trained it. Not because it does Fourier transforms. That's not the reason why it does that. The reason why it does that is because if you look at their Jacobians and you look at their eigenvalues, their largest eigenvalue is smaller, which translates to more diffusion in the Fourier spectrum. So the magnitude of the largest eigenvalue, the closer it is to the origin, the closer the arrow is to the origin, the more diffusive the system is, which is why you see you capture a larger portion of the spectrum. You have a large spectral bias, by the way, in this particular system because it's a stiff system. But compared to two models, the one in this color, I'm colorblind, so I'm just going to call it orange. This orange colored model has better spectral representation. Why? Because its eigenvalues are smaller compared to the, whatever this color is, blue colored model. So the eigenvalues are actually predictive of this holistic performance of any of these models. Finally, there's a small story here as well, that there is a catch in this theory. Generally, when you look at physical systems and do linear stability analysis, so if you're doing hydrodynamic stability, you look at the linear stability of an operator and you look at how the eigenvalues decay, you have a decaying spectrum generally. So generally, eigenvalues show a decaying spectrum. In this case, the models do not show a decaying spectrum, right? All their eigenvalues are clustered at 1. So that's why sometimes for very close models, just focusing on lambda max might be problematic. So an extension of this theory is that instead of just looking at lambda max, what you need to look at is lambda max and the projection of the eigenvectors onto the residues. Because it might happen that despite you have a large, basically lambdas, all of these lambdas are roughly the same. So even though there is a numerical lambda max, they're not that different from the smallest lambda max. So it might happen that the largest lambda max have a 0 projection on the residue, while the smallest lambda max have a large projection on the residue, and that effectively increases your error. So basically Et plus delta T is impacted not just by the lambdas, as is typically the case for hydrodynamic stability and sort of physical systems. It is actually impacted by the projection of the largest eigenvector onto the residue as well. So based on that, you can actually design a loss function that promotes stability, which is instead of having L2 loss on your error, what you write is you basically write your Jacobian operator's projection onto the previous time steps error, and you match that. You basically want to minimize that. What are you trying to do when you train your model? You're trying to minimize the error at the next time step. You're predicting one time step and you're putting an L2 loss on that, which means you're trying to make sure that the prediction of your next time step matches the true next time step, which means the error at the next time step should be small. So let's calculate the linearized version of this error, which is Jacobian times ET, and penalize that. That ensures that you're essentially bounding the eigenvalues as well. An example of the first case where you may have larger lambda max but smaller error because of this projection can be seen in this plot, where this model, the model on the bottom, which is a better model, has a larger eigenvalue, but these eigenvalues have roughly 0 projections, very small projections, as compared to this model, which have larger projections, which is why the error actually grows. And finally, if you implement that loss function, all these these legends might seem illegible, but the purpose of it is to make them illegible, which means that across many, many models, these tests have been done that shows any of the dashed lines, which dashed lines means where you have a linearized error that you're optimizing for instead of L2 loss, have lower error growth generally and more stability, no matter what the architecture, no matter what the integration scheme, as long as it's some into at least order 1 integration scheme. Okay. So this was about distilling out a theory from the essentially this algorithmic intuition that we had. Having an integration scheme should make this closer to a numerical scheme. And sort of the question that we asked was, does this intuition make any mathematical sense? The answer is yes, at least to the first order it does. It conforms to linear stability analysis. Stuff that we learned about implicit explicit solver holds up. We have a diagnostic tool now to decipher between models. So if tomorrow someone gives you a giant transformer and someone else gives you a diffusion model, none of them that you can scroll through the code and understand what they're doing. As long as you have access to its derivatives, you can tell me which model is going to do better. And that's operationally all we want. So it's a practical theory in some sense, and it conforms to generally LSA. So any questions up till here?
Questions? Yeah.
That's a very interesting analysis. I have one question is, can you generalize it in terms of, so these errors, what you are talking is in terms of wave number or it's a frequency? So one of your earlier slide, you said the high wave number where your A is actually moving, diverging away from these things.
Correct.
So it intuitively means that the low wave number, like the climate scale systems, which are like say MGO or maybe or whatever is the lower wave number, they are performing well in the model. In
Right.
terms of prediction, I am thinking that then their predictions should be easy, but it is actually not. Okay, the GraphCast or the ForecastNet, whatever their success is in the prediction of extreme events, for example, very local extreme event, which in terms of Fourier analysis, I will say that it is a high wave number system. So how to reconcile these apparent differences?
Okay, actually, yeah. So let me clarify a few things as well here. So ForecastNet, GraphCastNet success is in terms of statistical metrics that they look at over multiple different variables. You're absolutely right about that. Even for extreme events, I wouldn't say that any of them are really successful, because if you're really looking at long-tailed events, none of these models capture that for the right reasons as well. But what they do get is some sense of what the trajectory of these extreme events would be. Like if there's a tropical storm, like a category 5 tropical storm, they get the trajectory right, but what they do not get is the intensity of, for example, MSLP. So then they're not perfect either. Now, coming back to your question again, so now that I'm talking about this error, what am I really saying? Is this error at the low wave numbers, or is this error at the high wave numbers? Now, intentionally, I am not decomposing this error into either low wave numbers or high wave numbers. Why? Because I'm looking at error as a function of time. The problem with these autoregressive rollouts is that although at time step t equal to 0, if you look at GraphCast again, although at time step delta t, all your errors are from wave number 100, for example. All these models have errors only from wave number 100. By day 10, some of these models have now errors starting from wave number 0. So with time, the decomposition of error in its Fourier space also changes. So if we have to have a predictive theory, then it has to be on the total error. It shouldn't be reliant on the Fourier transform of the error at that time step, because technically you don't have access to this error, right? All of this is post hoc analysis. I can plot errors if I have access to the truth. So the goal of doing that error analysis is coming up with a priori diagnostic measures. So what I'm trying to say is that if my model were to conform to linear theory, then your model performance, no matter whether your error is in the high wave numbers or the low wave numbers, would be governed by the magnitude of the largest eigenvalues and the projection on the projection of the residue on the largest eigenvector. It doesn't matter whether the error is in the high wave numbers or the low wave numbers, because for some models, for example, for the direct step model, that error is in the low wave numbers. Like you said, it fails to capture even the large scales. So that's fine. And that's why you have a large lambda max, a very large lambda max, which causes the RMSE to grow up very quickly. But for the other more subtle ones, where error is not growing so fast, here actually the errors are mostly concentrated in the high wave numbers. But still, the slope of this error is proportional to the largest eigenvalue. So at t equal to 0, with the initial condition, if you calculate this metric, you would be able to discriminate between these two models, and more importantly, between these 32 models that are overlapping with each other, just by looking at this lambda max values. So that was the general idea. Does that roughly make sense?
Any other questions?
Yeah. So when you're projecting the eigenvectors on the error, this slide basically, shouldn't we not ignore the largest eigenvalues, because these might be like the previous question asked, these might correspond to some rare but extreme events which might be significant.
We absolutely cannot ignore the largest eigenvalues. It has to be a combination of both the largest eigenvalues and this projection. The cool thing about these models are that there is no such thing as a largest eigenvalue. Basically, your lambda max is the mean of your trace, because the eigenvalues are roughly 1 plus minus 10 power minus 7. So so you really cannot ignore the largest eigenvalue. None of them are 0. They cannot be mathematically equal to a small number. They have to be 1 plus minus something, and that plus minus is a small number. What you really have to look at is just the projection operator. So it's like a two-phase diagnostic. You look at lambda max. If between two models, one lambda max is 1.5, the other lambda max is 1.001, you're sure that the 1.5 model is bad. There's no doubt about it. There's no way this will change unless the only thing you have to check is that the corresponding VI to that lambda max is not orthogonal to ET. Only then will that impact change. So that is the only thing you have to ensure, that it does not have an orthogonal projection. Otherwise, 1.5 would dominate over everything else. For models where you have both your lambda maxes are maybe 1.0001, 1.0002, that's where you have to go and check how the eigenvector, how the cosine similarity between the residue and the eigenvector looks like. If one of them is much smaller, then it would very likely be a better model, because your ET plus delta will be damped as compared to the other model.
Going from just the L2 now to this computing the max, then to this projection, we are basically focusing more and more on long-term stability. That's the goal, right?
Correct.
Which the models is more long-term stable.
Correct. And
will that not force predictions towards larger scales to be more important? Like it is always stable, has less L1 error, but it's always missing the small scale stuff.
Exactly, to account for the small scales, any of these loss functions will be accompanied by lambda times spectral regularizer.
Sure. Not so useless, I guess.
Not so useless, correct.
Anyone else? Okay, I think we can carry on, Ashesh.
Yes. Now, so now we have a theory, we have a nice algorithmic intuition theory. Let's do sort of the litmus test, where we implement everything at scale, see whether we can build a fully AI-based climate model. So climate model is more than just long-term stable. It needs a few other things, right? So this is what a climate model should ideally look like. It should have a bunch of variables. It should have basically all the 3D variables. Technically the ocean as well. It should have carbon dioxide as one of its forcing. I should be able to turn a knob here. So at this point, now that we have some semblance of a theory and some initial progress, let's think like an engineer, or think like someone in an operational center. And I'm not a climate scientist. Here's what I want to do. I want to turn a knob and look at projections. That's literally what I want to do, right? That's what a climate model is for. We should have a forcing from solar radiation. We should have things like orography and so on and so forth. So we call this Lucy. Lucy is our very, sort of humble attempt to build something cheap at scale. So in many ways, it's low resolution, minimum HPC requirement. It can actually be trained on 2.4 hours on a single A100 GPU. More importantly, if you look at the paper, which is the first Lucy paper, I will show you that this can be trained with just 2 years of ERA 5 data. The underlying architecture is a spherical Fourier neural operator. It can be absolutely anything that you want. It really doesn't matter what this architecture is. By now, we have convinced ourselves. It matters in terms of whether your 3-day prediction is 0.5% better than whatever else is your state of the art. But in terms of physics, none of this matters. The way we train it, exactly the way we train weather models. If you're interested, and I hope you're not, this is what the SFNO architecture looks like. It uses Fourier transforms. These Fourier transforms have in spherical harmonics. These Fourier transforms have nothing to do with the physics of the system, okay? It is not a better algorithm because it does Fourier transforms. It does Fourier transforms because it wants to do computation in N log N. It replaces an attention kernel with a Fourier transform because it wants to do integrations more efficiently. Like, nothing about the spectrum of the physical system matters here, okay? That's not why it's a better model. Anyway, and what are the things that we have in this model? The same two principal structures: an integration constraint and a spectral bias. Something that fixes the spectrum. In this case, the spectral bias is actually implemented. The spectral bias correction is implemented on the tendency. Initially, in the previous work, we did this on the state. Here, we do this on the tendency. Why do we do this on the tendency? Well, we don't have to. You can do it on the state as well. You will have 1% difference in climatology. So we're trying to demonstrate our best work essentially. So in a nutshell, this is what Lucy is compared to say a traditional climate model. It is stable for decades of simulations. A quick overview is that it gets the annual cycle correctly. It gets the temperature cycle, the annual temperature cycles correctly. It doesn't need to be imposed with SSTs and so on. The cooler part is that you can run 100 ensembles of 100 years pretty much directly on your laptop. This is what it was meant for. It was meant for people like us who do not have extensive TPU resources to be able to do sandbox experiments. This is by no measure an operational climate model, although Lucy 3D is much more high resolution and satisfies those things. Also, these codes are online, so you can download it, run it, let us know how it goes. Next few minutes are not super important. This is, I'm going to show you a set of results that as a climate scientist you would want to see. These are not the end of the story for any climate model. People do years of more testing in more systematic fashion. This is basically a bare minimum litmus test, which is why I keep using this word, a bare minimum litmus test to show that this speaks like a climate model, this walks like a climate model, talks like a climate model, and in many ways represent the physics more accurately than any of the other AI weather models, none of which can be used as climate models. So this is without CO2 control runs. Top row is Speedy. Speedy is one more simple toy climate model. Lucy is the second row. Error 5 is trained on Error 5. These are the biases. As you can see, these are 100 years of climatology accumulated over 100 ensemble members. Obviously, the climatologies are very accurately captured. Even there's a dry precipitation bias. But beyond that, of course there are errors, but in general, Lucy does get the right climatology. It doesn't have any of the weird stuff that Pangu had, where equatorial winds were going off the chart in the equator and things like that. The major thing to note is that the precipitation, there's a systematic dry precipitation bias in Lucy. It's actually better than Speedy at the same resolution, but of course it is if you compare with Error 5, right? This model was trained on Error 5, so it's obviously going to look more closer to Error 5 than any other climate model for that matter. So you can compare this with any other climate model, it would look better. These are the zonal means, individual ensemble members means. You can see sort of the double IDCZ thing in total precipitation. Roughly the zonal means are accurate. It's obviously better than a traditional climate model. The other things to note here is spectra. We had imposed spectra we had imposed spectral regularizer on the tendency. So we first look at the tendency over the extratropics. So it was only imposed over the extratropics for these few variables. And then as you clearly see from between the unregular, so spectral regularizer, like Jim said, spectral regularizer does have an impact. It does not fix all our problems. You can see a consistent bias still, but it's better than having nothing. And that's the most important point to put. It's better than having nothing. The dotted line is without the regularization. The blue line is with the regularization. It does improve. Now, Speedy spectra looks terrible, but not because it's a bad model, right? Speedy spectra is terrible because, as we all know, all climate models have hyperdiffusion. This is basically hyperdiffusion, doing its thing. It's meant to keep these models stable. There is an overall improvement in the mean bias of climatology using these spectral regularizers. Again, now we look at the global states. The impact that having a regularizer on tendency has on the global states. Obviously, it improves but only very slightly. What has really improved is the tendency, and the global state, again over the extratropics, is improved only very slightly. What does happen, of course, is that it's stable long-term, gives us the right mean. This is probably something that some of you are interested in, is if you look at, I'm by no means an MGO expert, but people plot the Wheeler-Kalides diagram when they have to study MGO. This is the symmetric component from Era 5 and from Lucy. We had a long struggle getting the Kelvin waves correctly, but eventually we do. We have some notion of MGO, although not quite, and we sort of get the right spectra for the Kelvin and the equatorial waves as compared to Era 5. So this is one of the things that we wanted to really focus on, is that this is a test beyond climatologies, right? It's beyond the first order tests, like do we get MGO, do we have the right Wheeler-Kalides diagram and things like that. So this is one of those tests. This is sort of the monthly zonal precipitation, which is pretty accurate, matches with Era 5, not particularly insightful, except that we have a shift in the double ITCZ as you expect in the reanalysis data. So it kind of gets those things, although it's incorrect, but I mean, again, not an expert in tropical dynamics, but although it's incorrect, it actually captures these things. Some of the other things that we looked at is the variability in Lucy. We kind of get the right southern and northern annular mode. These are basically EOFs, or the left singular vectors, PODs, depending on which community you come from. The average annual temperature range is accurately captured by Lucy. Again, remember, there is nothing is imposed in this model except for control CO2, no change in CO2, and total incidence solar radiation. Okay, that's the only thing that is imposed into this model. SST is not fed back in. No SSTs are fed back into this model. Like true SSTs are not fed back into this model. Finally, we go to extremes. I want to take a minute to give a shout out to the first author of this paper. We wrote this recently, and the entire work was basically dissing AI models for not being able to capture extreme events. I got a question earlier. I'm not able to see who it was, but we got a question earlier about whether AI weather models, GraphCast, forecast, and whatever, they capture the really long tails. Especially, can they capture gray swan events? Gray swan events are essentially events that are physically possible but are not captured in the observational records. So the short answer to it is that no, it doesn't. And it doesn't because of number of different reasons, out of distribution generalization being one of them, but also because we would show how the dynamics of tropical cyclones in the extratropics and tropics are different, and how that impacts the learning of these models. So long story short, you don't get extreme events in any of these models if you have not seen them before. So no gray swans. You don't capture any of the gray swans, and we do systematic experiments to show why not. But then if you see some stuff on one basin, you will be able to recreate some of them in other basins. So you have translocation, you don't have out of distribution generalization. So after this paper, we did some experiments with Lucy to see whether we get extreme events that are indeed not there in our training set. So we trained Lucy on 10 years of data, the flagship model, but we unrolled it for 100 years, right? So can we get extreme events that we've never seen before? And the way to test that is, let's look at the return periods of extremes we are getting. And indeed, we do, let's say, simulate, and I'm going to be particularly careful with the choice of words here. We are able to simulate extremes that have return periods larger than the return periods of events that were seen in the training data. So at least that capability you have when you are able to unroll models for hundreds of years. That's the other reason we wanted to do data-driven climate models, right? We wanted to run thousands of ensembles and get good uncertainties on extremes that were otherwise not possible with the kind of data we had. And here you are able to simulate these. This by no means, and this is, by the way, simply not possible with any of the AI-based weather models. So if you read this paper, go back and read this paper, what we would show is that any of these models would only reproduce extremes in the range that they've seen before and cannot do anything outside that. Here you can. This by no means says that this extreme event is a physically consistent one, that something like this would even happen. So that requires us to do far more testing to be able to ensure that. but at the very least, we were able to simulate temperature anomalies that were simply not there in the training period of these models, okay? So if you have more questions about this, please ask me. I'm not saying we get extremes that we've never seen before. I'm saying we can at least simulate extremes that we've never seen before. Whether or not it's even a meaningful thing is, a separate question altogether. Finally, we start doing things like, let's change that knob. Let's slowly increase CO2. So first, let's put in observed CO2 and see whether we can get the trend, the temperature trend that you typically see in era 5. Then let's increase CO2 to 4 times, like 4 times our current CO2, and then 8 times, and things like that. And long story short, observed CO2, we get the era 5 trend correctly. So again, my issue with this slide is that I'm colorblind, but Lucy is this red line here, the temperature trend. Era 5 is the blue line. If you turn off CO2, you would essentially get one of the horizontal lines, which means that your temperature will not show a trend as is expected. So this part of the model actually works pretty well. Then we look at things like between 10 years, like 2 simultaneous 10 years of simulations with climate change, whether we get the structure of the climate, whether we get the structure of the dynamics correctly. And we do, like in the tropics, at least we do. In the troposphere we do, what you would immediately see is that our stratosphere is terribly off. Basically, our zonal temperature change, while it matches with era 5 in the lower altitudes, is absolutely incorrect in the stratosphere. And this is further validated if you look at the temperature trend in the stratosphere with an increase in CO2. And there could be many different reasons. One of them is the absence of data. But we get something, we don't get the accurate one. So we actually went and did some more testing on stratospheric SSWs, are stratospheric sudden warmings that happens because of the polar vortex breaking and so on. What we wanted to see is whether we're able to emulate some of the SSW events that era 5 has seen. Now, era 5 might not be the best data for this either, but basically what we see is we have a early my mistake. We have a late detection or late emulation of SSW. So it's essentially lagging behind what the true observations show. However, we do get SSW events. So it's not that the stratosphere is completely unphysical. It doesn't quite match with what we expect, and it doesn't really line up with era 5. So while this climate model is super exciting because it's really like a push of a button climate model, everything in there, there's still certain things that we don't have, and stratosphere being one of them. Some of the other things you can do with Lucy is that if you're into paleoclimate, you can spin this off from a 0 initial condition, and it would go up to climatology after a year. So it behaves like a climate model in that sense, right? When you do ocean-atmosphere interaction, ocean-atmosphere coupling, spin up the ocean for a while, and then it catches up, and then you couple it, right? So you can do these things with Lucy. You can spin it off from climatological initial conditions, and it would still, spin off to climatology. So basically, initially, a 0 initial condition means you don't have. 0 initial condition is unphysical. It means there's no atmosphere. You just have the forcings, and then you just run Lucy for 100 years. Within a year, it would spin up and get the climatologies correctly. Similarly, you can do this with changing in CO2. So if I keep the CO2 constant from 1980 to 1990, you see that you have a low temperature bias. If you run this with the correct CO2, which is the higher CO2, then you have the right sort of temperature. The bias is in the right direction. So you can play these games, or you can run these experiments where you're thinking about scenarios, basically addressing the scenario uncertainty block of that diagram, where you want to look at scenarios with different types of CO2 forcings. If you had the same CO2, what would happen if you didn't have this, and then run hundreds of ensembles of it. Anyway, so I'm going to try to wrap this up with a few trailing thoughts. There is some more work that we're doing, one of them being on high resolution regional oceans. These are some of our papers that feel free to, that you can go and check out. One of the things that we have is something called OceanNet, which is sort of our high resolution version of the regional ocean, similar to sort of Lucy, it's long-term stable, very accurate, outperforms ROMs, like state-of-the-art numerical ocean models. Then we're doing things like addressing sort of the whole pipeline in any of these modeling tasks where, you start from observations, go to initial conditions, then you go to the actual AI emulator. And a big portion of it is data assimilation, especially for Lagrangian observations. So feel free to check these things out if you have the time. Okay, so with that, I'm gonna stop, and I'm not sure if I have time for a few questions.
Okay, thanks a lot. Thanks a lot, Ashesh. This talk really highlighted or explained many of the fundamental questions related to AI-based weather forecasting, and many of the questions which I think which many of us had about like the limits of AI-based weather forecasting and why those limits are there. I think we developed, many of us got an idea of the answers to those questions. So questions from the audience, yes.
Hello, sir. Sir, you have mentioned one thing, just all the climate models are hyper diffusion models. So what is hyper diffusion model?
Okay, no, I meant to say that all climate models have, in some sense, a hyper diffusion term. So, let me explain this. In geophysical fluid dynamics, in most cases, you don't have molecular viscosity, right? You don't have an explicit Reynolds number term. So to account for the curl up in your energy spectrum, what you do is you have an 8th order Laplacian or 4th order Laplacian on the right hand side. Instead of diffusion, you have a higher order Laplacian which serves as hyperdiffusion. And the way you implement it is that you don't actually solve the 8th order Laplacian in Fourier space. What you really do is that you solve for one time step without a diffusion term. Then you take that state and you filter it. You say that I'm going to cut off everything beyond a particular wave number. That's how you implement hyperdiffusion. What that enforces is that the high wave number part of your spectrum, which are not accurately captured, right? It's not a DNS simulation, so you're not going to capture it. What happens is that the high wave number part of the spectrum is diffused out, and every time step you repeat this process. So basically, if you Google hyperdiffusion in 2D flows or like geophysical fluids, there's a lot of work around it, and it's a standard thing that almost all models without molecular viscosity, even models with molecular viscosity, sometimes have these additional terms to account for subgrid scale processes. So another way to understand is that, how we learn about parameterizations, hyperdiffusion is the silliest parameterization of your subgrid scale stress in the momentum equation. Hopefully I said that correctly. Probably many more GFD experts in the hall that can rectify me if I'm incorrect.
Okay, sir. Thank you.
Yeah. Yeah. Sorry, by the way, just to clarify, I'm not Jim, I'm Mayank.
So sorry. I can't see the audience. I couldn't tell. Sorry.
It's fine. We work together, so it doesn't
Yeah,
matter.
yeah.
So, yeah, in all of these analysis that you're showing, you're saying that the model really is not that important, whether you use an FNO, you use some convolution based. But wouldn't it sometimes be useful because, for instance, having many local, because the Earth models, the Earth is inhomogeneous. There might be some inhomogeneous factors. For example, things work differently near Atlantic, near Bay of Bengal. Wouldn't it be interesting to add some architectural changes so that this inhomogeneity is captured?
Yeah, I mean, I still agree with this. I mean, what history has taught us, at least in this field and other fields where deep learning has gone into, is that while these things make sense, like you're absolutely right that there are inhomogeneities in your domain. You should have domain-specific models that interact with each other. And for example, if you know that your system is rotationally equivariant, have SO3 equivariance into your model, and people have done that and they've showed great performance. At the end of the day, what has really stood out is that if you have enough data and you can really scale your model, like vision transformers, there's nothing no inhomogeneity capturing stuff there, right? As long as you can scale it up with enough data, at least physics-wise, there doesn't seem to be any difference. So I think I agree with you that it makes sense that if you know something about the physics, why not put it in there? What history has taught us is that if you have enough data, it'll get learned. So now it's really a question about whether we should think of physical constraints in the same sense we did before. That's why the kind of constraints that I work on is something more fundamental and not geared towards particular physics. It's something. So I should also clarify myself that it's not like the architecture doesn't matter at all. MLP and FNO has two different spectral biases, like I showed. What I meant to say is that physics-wise, there's no difference. Both of them are long-term stable if you have the right kind of constraints. If you have the right structure, both of them are stable. And the difference between these two architectures, the performance difference, like there would be a 2% difference between MLP and FNO and vision transform and whatever. This should be diagnosable. Like that should be the outlook towards modeling, right? I should be, I definitely cannot interpret any of these models. I mean, there's no such thing as interpretation is really in machine learning models. It's you tinker with things and you look at saliency maps. None of them mean anything to a physicist. I should be able to say something, predictive about its behavior from diagnosable quantities. That's the only sense of interpretation that I should care about. So if that says that it will be 2.5% better than an MLP, sure, be it, as long as I'm consistent with this, with this statement.
Diagnosis part where we compare different models, that was a really nice and new way of looking. Thanks a lot.
Thanks.
Any other questions? Yes.
In your Lucy model, did you check it that MGO spectrum you are getting, but Kelvin wave is weak? That's quite interesting. But again, it's not a physical model. So suppose if you project your MGO U200 or any onto the observed thing and do a principal, do you see the eastward propagation and other things? Has anybody checked that?
We have. I totally know what you're saying because we used to work with a few NGO people who wanted to do this as well. We have not been able to do that. To be fairly honest, we're not, big time, tropical dynamicists or any of that. But the Lucy code is online. If there are certain experiments that you feel it should go through, then it's suggestions that we would like to take and also incorporate into our model. We have absolutely not checked that. Although I believe that we will probably not get these things super perfectly either. Like for example, we can also check those indices that NOAA gives us, right, for the MJO, or whether we get the phases right or not. We really haven't checked any of these. But
another bias in the climate model is like a cold bias in the upper level. So you saw some plots. I saw you showed, but I did not get it. So do you have cold bias in the? There was a latitude versus height plot in your one of your slide. Yeah.
This one?
Yeah.
Yeah. So this was, let me explain. This was basically looking at the changes in zonal moisture and temperature from the 1980s to 2010 for ERA 5 and Lucy. So we are basically just looking at the change because of the impact of CO2. And so you're saying which cold bias?
No, I am saying that
cold bias in the stratosphere, but that is an incorrect one.
Okay. No, in normally CFS V2, which operationally in India is used, it has a upper level cold bias, which we struggled to get the subseasonal structures correctly because of that.
I see.
So that's why I asked. Okay, we'll check. Thanks.
Thank you so much.
Hello, sir. So it's Sreyashi. So I wanted to ask that all those GraphCast Pangu weather, they took days and TPUs to actually train them. So if our focus is training them on some region of interest on a university level, how much of computing power would it require?
So the two answers to this. One is like if you're training this model on regional data, first of all, there's no guarantee that it would even work. Like many of the tinkering there is because it's global, it's periodic, they've gotten away with a lot of things. Like for example, ForecastNet V2, which uses spherical harmonics for the Fourier transforms, they assume that you have a periodic domain. So as soon as you do this regionally, you're bound to get screwed. So like before even thinking about computing, some of these models might not even be suitable to be trained on regional scale data. Now, in terms of computational resources, you can train versions of GraphCast at lower resolution, globally, at lower resolution, if you change a few different things. For example, if you remember, GraphCast actually unrolls its forecast for 12 days before doing backpropagation. To give you a sense of how much compute that is, if you have 1 billion parameters, then 2 unrolls means you have 2 times the memory of 1 billion parameters. Sorry, 2 order. So basically, if your memory is M for 1 time step prediction, if you want to do 2 unrolls, your memory now becomes M squared. So 3 unrolls, your memory becomes M cubed. So 12 unrolls means your memory becomes exponential in memory. So what you can do is you do not need to roll it out for 12 days. If you don't care about GraphCast level performance, you can roll it out to a couple of days, and then just training on regional data, you have already reduced not the resolution, but you've reduced the amount of memory requirement per batch. So if you follow just these 2 things, you would be able to train GraphCast at with like 8 or 16 GPUs, say for example, at a university scale computing center, without tinkering with the architecture. Of course, you can also do things like there are 12, or maybe this number is incorrect, or maybe it is not, 12 levels of meshes, right? Because they do, each of their meshes are further fine-grained into finer meshes, right? That's how they generate their multi-meshed graph model. You can reduce the level at which you're doing the refinement. So that would also still not tinker with the architecture. It would have an impact on the performance, but you would still be keeping the generic architecture the same. So, but you would reduce memory requirement and be able to train GraphCast. So.
Hi, sir. Nice talk. So my question is regarding the spectral bias. So I saw the models that you have used, they are purely data-driven models, right? So have you also looked at some of these hybrid AI models like Neural GCM?
Yes.
Do they also show something similar where you have your...
Right. So let me clarify. So these hybrid models, so particularly Neural GCM. So I have a picture here with a hybrid model. It wasn't Neural GCM because this work was way before Neural GCM stuff. Yes. So this paper is by Jaideep Pathak, who was also our first author in the ForecastNet paper, and you can find this. So this was a hybrid ML model for the Rayleigh-Bernard system, and you can still see a spectral bias. Now, for hybrid systems like Neural GCM, depending on what, so you can see the bias here, right? To answer your question, yes, hybrid systems would also eventually show spectral bias, but there are a few things to keep in mind here. Your primitive equation solver, Neural GCM is what? It solves the primitive equations like any other standard climate model. All the parameterization, ad hoc parameterization stuff, they say it's one big giant model error that I will learn from data. It's one forcing term added to the tendencies that takes care of everything, vegetation, land feedback, everything from error 5 data. That's what the model is, right? Now, if the primitive equation solver has hyperdiffusion, for example, then obviously it would have spectral bias. But there's no concept of spectral bias for a numerical solver. So what you will see is the impact of spectral bias coming just from learning the model error term with a neural network. So at one time step, it would probably not show up if you were to train that model this way. But Neural GCM is trained online. It's trained again like for 12 time steps. So it will definitely show up there. But it might also show up because you have a hyperdiffusion term. But then that's not really spectral. You kept it there, so you can't complain then. But the spectral bias coming from just the parameterization term will show up. So if you look at that Rayleigh-Bernard paper that I put, if you Google Jaideep Pathak and Rayleigh-Bernard, you'd find that paper. They have a much simple system where it's easy to see these things without like looking at 1,000 lines of code, and you can see that there will still be spectral bias. And they did not have, well, they did not have, actually they did have a hyperdiffusion because it's a really bad answer. Anyway, go on. Thank you.